Welcome everyone. Thank you for attending. We have today Johannes Jakubik from IBM Research presenting. Johannes is spending a few weeks, months with us as a visiting researcher, and he will present about his work partly at ESA. We'd like to say no, at IBM Research.
No, partly at ESA. I think that's good.
So enjoy everyone. We'll leave the word to you.
Okay. Thanks for joining everyone online and in person. I assume that for some of you people in person will be kind of a repetition, but I framed it differently, so maybe we'll see it out of a completely different angle and it will be a super enriching talk, and if not, then it's just a repetition. Since the last time I gave this presentation at the beginning of my research day, we got a new Turing Award, so we changed the 6 to a 7, but the rest is the same. So we are still around 3,000 researchers, and we are around for about 80 years. In a couple of different locations. Okay, we do a lot of geospatial work, but actually our unit is called planetary computing. So we primarily work with the European Space Agency in Earth observation, but we partner a lot with NASA in planetary observation. Also maybe because of the current administration in the US, there's a bit less focus on planet Earth and a bit more focus on Mars and the moon and stuff. We work a lot on Luna. We released a heliophysics model a couple of weeks back, and so this is kind of, broadly speaking, what we work in deep learning. Okay, why should I care about learn quantization? Basically, after this slide, in principle, you can leave the talk if you feel like, but you would hopefully have an overview on why quantization is something that is interesting. So the first thing is, if you quantize representations, you can natively translate between a lot of very different modalities, because quantization basically means you are representing any kind of information as discrete integer representations. You could do that with a time series, you could do that with text. It's what language model people do all the time, right? And you can do that with any other kind of data representation too. The question is how good you can do that, and that's part of the work I'm doing. I'm trying to understand how we can learn quantized representations really well. And the moment you have them in an idealized scenario, you would have a compressed data representation that is very versatile in the sense that you can translate between a lot of different modalities. Then there's another aspect that I summarize under stability of the training. So basically the idea is, if you predict something with the deep learning model, it's usually easier for the model if this is a discrete representation. So if you have a lot of variety in your data that you're predicting, it's often helpful if this is a discretized representation. Let me give you an example. If you pre-train a ResNet model on ImageNet 21K, it will learn pretty powerful representations, and that's work that is 5 to 7 years old already. And one of the reasons behind that, in my opinion, is that in ImageNet 21K, which is a computer vision data set, you have 21,000 different classes, like cats, dogs, cars, whatever. And the model has to learn to classify against them. So it will have a pretty rich target space to train against. But we don't have that in Earth observation. We don't have that in heliophysics. There's no such way as a classification of an image in a very diverse set of classes. So if you leverage quantized representations, basically you have a somewhat abstract concept that you can train against. We will look into that in a second. Then there's a couple of questions on how you do state-of-the-art quantization. And I don't think that there's a good answer, but you always know that you will have some kind of a compression in this. And this compression will give you an additional error compared to normal autoencoding in deep learning. So there's a question on how you can minimize that error. This is basically what I try to do in terms of the quantization itself. And these other areas are more where we try to apply quantization. Lower left, when you do quantization, as I said before, you're training against quantized representations, and that often helps to structure the embedding space a little bit better. So we often see that the embedding space forms nicer clusters for us. And then this is very ongoing research. The fifth point, quantization can unlock a couple of new tasks for you in a sense that, as I said before, it kind of goes hand in hand with the first bullet point. If you have a quantized representation, as you can translate between very different data representations, often use different data representations for different tasks, you kind of unlock those as well. Now you will see how bad I am at PowerPoint because I tried to morph these 1, 2, 3, 4, 5 bullet points into the areas of the work that we will see in a second. So think about this would be a morph. And so for the upper left, when we have a look at a recap on TerraMind, basically it's influenced by the points 1, 2, and 4 from the previous slide. And so do the others. So basically, I will talk you through a couple of examples and our previous work or our ongoing work. And it will basically boil down to give you an idea on how these different things are actually then tackled by the work that we do. Okay. Any questions so far? It was really abstract, so probably no one understood anything. Or you already know everything because you attended the last seminar. Let me give you a very quick recap on TerraMind. I think that's probably the most boring part. Basically, TerraMind was trained on TerraMesh. It's a quite multimodal data set. At least at the time, it's like 1.5 years old. So we had a couple of different data representations, and we are kind of asking ourselves the question, how can we now translate between those? How can we make sure that a model digests those different representations? And just to come back to what I said before, let me give you a quick overview on what's happening. So we have these different kind of input modalities, and then we have pixel level input. This is what you would usually do in most VITs, right? You would patch file your data, and then you have some 16 by 16 pixel representations, and you would patch embed those. You will get a latent representation that is also a floating point. So this is standard world. Then for this, it's kind of what we proposed on top. So basically we said, oh, maybe it's a good idea to have a discrete representation also on the input side, where basically each patch is represented by a single discrete number. Like this would be integer 4 and that would be integer 7. And so if you mask out, it's much easier to learn the correlations between these modalities, because you would basically say every time I'm masking the 7 and I'm seeing a 4 here, I would predict 7 because I kind of learned that. It's much easier than in a full 16 by 16 pixel cube to reconstruct all of the individual floating point numbers. And the second benefit is that if you have very different data representations like sequence data input and so on, learning correlations here between different integers is much more natural than learning the correlation between the first word of a sentence and the first patch of an image, which not necessarily needs to be related. And then on the target side, to stabilize the training, we are only predicting the discretized token. So basically you boil down your problem to a classification problem in a somewhat well-defined set of concept classes. Okay, so that's basically, just to summarize again. So we said we are stabilizing the training. This was point 2 from before. We said that we can learn across very different representations. That was point 1. And let me double check what I said for point 4. Point 4 was, desirable clusters in the embedding space. It kind of goes hand in hand. So the moment we are training against these concept classes, the model will kind of understand every time I'm seeing this pixel patch, I'm seeing this tokenized representation. So natively, you already force a clustering in your latent representation of this model, because you condition your input that you have here on some kind of a latent representation. It's quantized latent representation, but in principle, it doesn't really matter. So just because I had this conversation, I think a few days ago, the idea of CHEPA, for example, is different, but this is also latent space prediction, right? Because all of these quantized representations are basically unimodal latent spaces of all of these different modalities. I think this is really a very different angle to see this. So quantization is basically, in some sense, a bit like CHEPA, because you're predicting latent representations. The difference is that those are discretized, and by doing that, you have a couple of properties like learning between different modalities and so on. Okay. Then the question is how to come up with these quantized representations, and actually this is some of the most interesting work, at least to me, that I've been reading in the last 6 to 12 months. There's a couple of really cool research going on in this context. And you can think very freely in some sense what you're doing here. So I mostly wrap my head around what's going on here. And let me give you the general idea. So you have a raw input that can be any kind of unstructured data. It can be a time series, text, and it can be images. For text, probably the most simple thing that people do is you have a lookup table. You say word hi is integer 1, word I am, like I apostrophe m, is integer 2, and so on. And this is how you can discretize the information, and you can plot that to any kind of a transformer. What we're doing here is basically we say we cannot discretize a patch so easily, so we need some kind of a mapping to a discrete representation. And you could probably come up with some kind of a threshold-based binning technique, but it's not really promising. So what people usually do is they come up with a latent representation. You can use any kind of a backbone there. It can be something convolutional-based or something transformer-based, and you project that into a latent representation that will give you the standard, whatever, 768 embedding dimensions. And then you need to discretize that latent representation that you have for each token. So how you do that is you, for example, in finite scalar quantization, project that into a hypercube and you do nearest neighbor there. So you would say our patch lands in this red little box in the hypercube, and then you do nearest neighbor to all the corners, and you would say, oh, this is corner 4, and then your integer representation would be 4. And then this patch would be assigned to some codebook value. And what the decoder then does, it doesn't have to be diffusion, is basically it is receiving mass tokens. It is conditioned on the latent representation, which is integer 4 in our case, and then you learn to reconstruct whatever kind of patch. And I really want to encourage people that after this call are hopefully super excited about quantization to look into this area, because there's a lot of cool things that you can do. In the beginning, people did vector quantization. The idea was primarily you have a codebook and you would want to assign every patch in an image to that codebook. So that's a pretty naive way how to do it, but it's somewhat performant, but it's not end-to-end differentiable. So if you want to train that in a neural network, you need to introduce a new loss. Introducing a second loss typically makes convergence a little bit harder, so everything is a bit more bumpy. People came up with finite scalar quantization, not because it's better, but because it doesn't require the second loss, because it is end-to-end differentiable. Then there are questions around when does this codebook collapse? When is it too small or overused? So I think you can spend a lot of cool work on that area, which will be pretty fruitful. And basically, go ahead.
When you say finite scalar quantization, you mean always the hypercube, or it's okay?
Yeah, it's always a hypercube.
And it's differentiable because during differentiation, you sort of train the continuous values.
Yeah, you don't need to have a step
just because
stairwise.
The integer values are a subset of it.
Yeah,
so
you just use them afterwards, but you can operate on floating point representations. Exactly, you don't need to discretize. Cool. Well, good questions. No, I like that. Basically, as I said, I will present pretty much the same thing. So if you see it at a very different angle and ask different questions, that's really good. Okay, so basically, I think the general assumption here is that you want to discretize something. We learned that. It's really important to understand that you want to make sure that the error that you're introducing by the compression step when you're going from the latent representation to the discrete representation is as minimal as possible. And there are a couple of questions on how to do that. And it's also mathematically clear. I don't think that I have it in this presentation, but there's some kind of theorem that basically shows that if you would auto-encode here without the quantization step, this will always give you a lower bound compared to introducing quantization, which makes sense, right? You have a compression bottleneck that you cannot really overcome. So basically by that, you're introducing an error and you want to minimize that error because the quantized representation having a couple of nice properties, but the worse they are in terms of this additional compression error, the worse it ripples down in all of your downstream applications and model development. I'm spending way more time than I thought on all of that. Should just be a quick recap. Let's make this slide very simple and do that very quickly. So basically we train with these tokens. Next slide. You kind of know that, right? So then we see what we already saw on the left side. We basically train a model on the quantized representations alongside unquantized representations. On the right side is what we can do with that. We can look into generation, fine-tuning, and thinking modalities, which is a combination of the two, which at the time was quite an innovative idea. Let's have a look at how we can use the idea of quantization in the context of data that is not images. So we said in principle we can quantize everything. Time series is a very simple example probably. Think about it as a temperature sensor. You have a temperature sensor somewhere and you're interested in correlating the entire time series of that sensor to the patch of an image. But you don't necessarily have the image in all of these time steps that you measure the temperature. So in one dimension, you're spatially dense and temporally sparse, or you're temporally dense and spatially sparse. This is kind of how you can think about the data cube, and then you want to learn correlations within that. And given that this is, in the most extreme case, you just have a single satellite image, but a multi-day sensor time series, this is really sparse. Learning correlations, that's not trivial. By doing that, what we realized, which is how we motivated the work originally, if people learn correlations between satellite images and time series data, up until the time we released that, they did it in a supervised way. Now, at the moment, they are looking more into self-supervision, and that's kind of what we propose in this work. So basically what we did was we looked at the time series and we thought how you can discretize that. Obviously, you can do something like binning, where you just say all values over 25 degrees would go in that bin and so on. You can also learn that, which is finite scalar quantization. And then basically you would leverage kind of the very same model afterwards. Like after you quantize the representations, we just use plain TerraMind. So in that sense, this is what I like about quantization. The moment you brought it into a quantized representation, we just throw it at TerraMind and see what happens. It might sound a bit naive or stupid, but the more you think about how you represent your data in this discrete representation, the more uniform you can use it afterwards. And I think that's really a powerful thing about that. And then we tested it in a setting where we had a satellite image at the red vertical line, and we wanted to generate temperature time series on our GFS on the entire globe. So basically what you see in blue is the actual temperature, and in purple dashed you see the generated temperature. And you see that the model seems, even though it only has a single timestamp satellite image, it seems to understand, given that there's no big left to right shift, which time the image was taken. Check it again, sorry. I'll fix it afterwards. So there's no big left-right shift. That means even though we don't encode the time of the day, the model seems to understand where it is in the temporal space. And we also see that there's no big up-down shift, which basically means that it kind of seems to understand where it is and what to expect in terms of the overall magnitude of the temperature. Also, temperatures sometimes fluctuate stronger between day and night in the desert, right? But it's less strong in major cities. So it kind of seems that the model understands where it is and when the thing was taken, and then basically it needs to predict a sign. After that, it's not super complicated anymore. Then obviously you don't want to use that for temperature forecast, but you can kind of see that if we do 12 hours ahead with the generation and the actual temperatures, that overall the picture looks reasonable. So the model seems to be able to learn a correlation between a single satellite image and a multi-day temperature that is hourly in this case, right? So that was one of the learnings, which falls in the bucket of we can learn correlations between very different modalities. We tested that in downstream applications. Now we'll again do my speech on gradients. I'm always advertising a book by Google DeepMind, which is a bit unorthodox because I'm with IBM, but there's a really cool book by Google DeepMind, which is called The Elements of Differential Programming. It's basically about understanding how to compute gradients, but then also a bit how to use them. So what we did here was we were looking at the CropNet task. CropNet is a data set where you want to predict crop yield. So you have satellite images and temperature data and precipitation data, and you want to predict how much crop there will be. And you can see in these radar-ish plots that here you have an RMSE, so lower is better. So here we are outperforming because we are the inner thing. And here our two scores higher is better. So we are at the outer side. So we are outperforming the models that were proposed for this task in the past. I think the more exciting part is the gradient analysis, where we really just looked into if you use the fine-tuned model on this task and you do one forward pass, then you get your gradients, and your gradients are kind of a measurement of sensitivity in some sense. So they kind of tell you how much the model output change when you have a fluctuation in the input. And what you see here is the yield prediction, and especially the error. We want to look at the error. So we see that we have pretty high errors that are around the US West Coast, while it's less pronounced in the Midwest and so on. And then here you see the gradients with respect to the image, to the temperature, and the precipitation. And you can kind of see that there's a certain level of correlation. For example, it seems that the higher the gradient of the image, the lower our error. The higher the gradient of the temperature, the higher our error, and same for precipitation. So it seems that there's a certain level of correlation between the gradient of the model, which was not computed against any real data, like any ground truth data, and the actual error of the model. So if you would deploy that model somewhere based on this pattern that you would observe here, your naive guess would be every time I'm seeing a high or here a low error of the image gradient, I would expect the error to be pretty large. So you kind of can think about deriving a sense of confidence. I'm not saying that this generally works all over the globe and the gradients must adhere to that, but at least here you can kind of see that there's a certain level of correlation which might be helpful to inform you how your model might perform in different environments where you have not tested it or you don't have data to do it. So Elements of Differential Programming, really cool read. Don't read the entire book, it's really long, but there are certainly sections that all of us will benefit from, like different sections for every one of us, but it's a really cool thing. And then gradient analysis, it takes you one day to come up with these, and often you see patterns where you're like, oh, that's interesting.
Small question, because I'm not sure I got it, but in this case, how can you say that this is due to the quantization?
It's not related to the
Okay,
quantization.
so because
No.
that can happen both with.
It's general to any model.
So you didn't try with for TerraMind with quantization and without quantization.
No,
Okay.
in downstream application, here we don't use any
Okay.
quantized representation. It's completely unrelated.
Okay, so no. Okay,
Yeah.
sorry.
I should have said that as a disclaimer. No, it's general.
Okay,
It's
okay,
plain computer vision.
No, that's okay. To investigate deeper into the relation between the gradient and the error, like some statistical tests, etc.
Statistical tests we did, also for the generations of the model, but we haven't looked into any causality thing. And I also don't really think that there will be causal relationships there. I think it's pretty much mostly pure correlations. But yeah, I think you can ask a lot of these questions like, how real is the correlation in different areas? How confident can you be in the correlations? So here, this is more a motivational figure rather than a full experiment, I would say. Cool. In the interest of time, I will speed up a little bit. TerraFlow is very similar to what we do in TerraMind generally. The only difference is that we now use multitemporal data, not in the sense of a time series of a satellite sensor, but in the sense of a stacked cube of images that are somewhat continuous in time, so a bit like video data. And I will move over that more or less entirely because from a quantization standpoint, the only thing that changes is how we cut the data cube. I will describe that for a couple of seconds, or someone else will. And after that, we can continue. So basically, we have two different ways of how we do sampling. One is random sampling, the other we call temporal disjoint sampling. The idea is that you derive tokens and you mask out a couple of the input and the target tokens. And then you have a clear cut for temporal disjoint sampling, as the name suggests, between what you input and what you output. So you can think about it like a video prediction. You would input a couple of time steps and you would try to predict what the next satellite image looks like. It's a very difficult task for multiple reasons, but it can be helpful to give the model a prior to be a bit more sensitive to how the image will change. So we we actually see that, I will go over the results because I really don't think we have a lot of time, but you can see that a bit if you do flood risk map generation. With TerraMind in the past, we got this. So if you got just satellite data input, Sentinel-2 and Sentinel-1, 2 time steps, and you would want to predict where a flood is more likely, and you had this as data to train against, then with TerraMind base, you would get this, which doesn't have any semantic information. And if you train in a temporal disjoint way, then you see that the model seems to understand that a flood is more likely to be around the river, but not on the river. And it's more likely to be in areas where you have lower digital elevation and higher digital elevation. It's very simple correlations that the model learn, but you can also see that the model does not learn that if you don't do this, let's say, forecasting step. So again, I think from a quantization standpoint, the main difference is that between TerraMind and this multitemporal version, scaling up in the temporal dimension is much easier if you have discrete representations, because the discrete representations require way less I/O. So overall, your data cube, you can fit way more data to the same GPU than if you would do the same without quantization. And you still see the properties that maybe you would want to see. I will try to spend a bit more time here because I think it's really cool work. And it's very much in the context of what we said in the beginning, where you have quantization in the middle and you want to improve the quantization. So this work is really about understanding that there is a compression error that you get with quantization, and you want to minimize that. Okay, this is the hypercube that you've been seeing before. So this hypercube is basically standard FSQ. So you have some kind of an image, and you encode that, you get a late representation. And then this is standard FSQ. We ignore the upper part for now. And then you would decode that and you would get to the original representation. So the lower part is exactly what we did before. Nothing changed. And then we said, oh, if you take a patch and you discretize that into a single integer, it's a bit like basis function decomposition, but only with the basis functions. So basis function decomposition, for everyone who's not super familiar, basically you have a function and you want to represent that function with a couple of sines and cosines. And you want to have a scalar factor that you would multiply with those sines and cosines. And if you take the analogy, then we are not doing that in vector quantization or finite scalar quantization right now, because we are basically taking a patch, we are representing that with a discrete representation like a sine or a cosine. This is like the basis, but we don't give the model any kind of capacity to have a denser representation that it can use to form something like a scalar value that it would multiply, not really multiply. I mean, we still learn it. It's not like a real multiplication, but that it can store information like the scalar to then improve the representation of that function. So basically, that's why we came up with the scalar amplitude tokens. So they are named scalar tokens because of the analogy to basis function decomposition, where you have those scalars, and it's basically just a single dimensional type of quantization. It's nothing super fancy in how we do it, just that we do it. That we split up the latent representation, and the model has this basis function part, which is the standard FSQ part, and we have this additional scalar part. And then what's kind of nice is we are testing that on very different data distributions. So we only trained on PDE data, and then we test on ImageNet data, on Sentinel data, on a couple of ERA 5 samples. So basically the idea is we want to understand if we only train on PDE data in that context, how well that does, and if it can generalize based on introducing this. Okay, I mean, probably you're not an expert in PDE data, and I'm neither, but basically this is the ground truth. This is NVIDIA Cosmos, which is a very generic tokenizer that was built for quantization. So basically the idea is that you can apply to any kind of data, and you see that they have a pretty high error on PDE data. FSQ also does, and we can kind of halven that error. I mean, in deep learning world, halvening an error is pretty decent, right? So originally, the main reason why we built that was that in this collaboration with ETH, there's an ETH AI Center PhD student that I'm supervising. He wanted to use FSQ because I said FSQ is the best, take that. And then he said, oh, for his application, it has not enough detail. It doesn't resolve enough detail to build a PDE forecasting model or whatever. So basically, he came up with that to lower the error of the compression that we're introducing. And what I said before on this compression error, you kind of see it here. So you would expect that the ground truth, if you train on that with a normal autoencoder without any quantization, this is the lowest error that you would get. And you compare Fedra against that, FSQ and Cosmos, and the promise of Fedra is to close that gap based on this intuition. That's the error analysis that I promised. Okay, this is super theoretical, but it's in the appendix of the paper, and for everyone who's a bit more like mathematical, maybe you want to give it a read. It's pretty standard if you think about it, but basically the overall conclusion out of that is that you have, with any type of quantization model, you have a loss. And that final loss will be bounded, let's say, by the embedding loss. This is the autoencoder loss without any quantization. And on top, the quantization loss, this is the compression error that you get on top. So we are basically trying to optimize that in the assumption that the autoencoding error is unchanged. Because there was a lot of work on that, we kind of assume that you cannot really push here, so we push there. And the moment a new autoencoding architecture would come out, you would kind of just transition. Okay. That works really well on PDE data. We saw that before. I think what's really interesting is to generally think about pre-training on PDE data. This is now not really connected to the concept of quantization. It's more related to the fact that after we pre-train on that data and we were able to derive tokens and to autoencode them, we were also able to use that model in out-of-distribution setups like here. So we pre-trained the model only on compressible Euler equations, only on PDE data. And then we tested the model on Sentinel-2 data. That's the input and that's the reconstruction. And I mean, it's as out of distribution as it can get, right? There's not much more out of distribution that you can think of, at least in my mind. And the reason why this works so well is maybe not from a physical spectrum perspective, but from a visual perspective. In PDE data, you have a lot of high frequency areas, and basically what a model learns that is having these scalar tokens on top is to resolve fine-grained functions, let's say. It's like very small areas, like if you would zoom in, then you would see that the model is a bit like, the reconstructions look a bit like painted. It's a bit like, like painted. So I found this really interesting. I'm not saying that this is necessarily the best performance that you can get. Maybe if you used finite scalar quantization, you could get to a similar performance, but it certainly indicates that it can generalize really well. So if you would pre-train this architecture on, for example, Sentinel-2 data, it would be very reasonable to assume that it works well on Phi-2 data. Same for ERA 5 down here. So basically that's PDE, like global temperature, and then U wind and V wind. And you can kind of see that the generation or the reconstruction there is pretty good too. So it kind of makes sense because this is kind of PDE data, right? At a very different resolution, but you would kind of assume that a model that was pre-trained on PDE data and sees very different PDE data might generalize to a certain extent, but here it seems to work even better. Okay, so this was with respect to how to push the state of the art in quantization. Actually, we just launched a new idea, Arthur. Can we call it idea? We're discussing an idea. Yes. With Arthur on how to fundamentally change that. So yeah, there are a couple of, you can think in more or less any dimension on how to improve that. And I think it's a really cool research field. There's not a lot of things going on, but the moment you have new tokens, you throw it at a model like TerraMind, which is open source, and you can play around with it and see what happens. So if you're kind of bored with whatever thing you do during summer vacation, think about quantization as a new hobby. And then open vocabulary semantic segmentation is kind of the last thing. It's in this presentation for two reasons. The first reason is kind of a call for action. Basically, all of the results improved based on having a new data set. So if you're bored after solving quantization, you can work on new data sets for Earth observation. The second part is that it kind of shows you in the architecture, we did not fundamentally change anything. And even though we never solved any type of open vocabulary semantic segmentation with TerraMind before, based on the concept of using tokenized representations, we can now approach it and it works reasonably well. Cool. First things first, for big tech research, it's always important to tell the other labs that their work is not working well somewhere. So we picked Meta with SAM3 and DynaV3 to say like an Earth observation is not working really well. I don't think it's super surprising. I mean, they train a little bit on Earth observation data, but it's not their primary focus, right? And you can kind of see that the baseline TerraMind model outperforms SAM, I think, by 3x, which again, in deep learning world is pretty much, right? Usually you talk about 5% improvement. Here it's 3 times as good as SAM, which is quite a lot. Still, the overall performance is not really usable. I mean, this is, I think, on average 35% MRU, which means for a real world deployment, this is way too low. But open vocabulary semantic segmentation is really challenging. So given that it has not worked at all in Earth observation, now it's working a little bit. And I will show you how we did it with a focus on both the data set, because I think that's really important, but also the modeling. Data set first. Basically, we said there's no pre-training data set to train open vocabulary models on, because you need a lot of different classes. And a lot of different classes, you cannot really annotate that. So the biggest data sets probably have around 200 to 2,000 classes. And here we crawled the entire OpenStreetMap archive and overture maps for entire TerraMesh, which is global, right? So we downloaded all of the masks that are co-located with the satellite images that we had for these areas. And then we did a couple of heuristics to select whatever class we do not want to include because of the size or the quality or something like that. And then we used the vision language model, Mistral Large, because funnily enough, Mistral Large is the only open source model that is out there for vision language. I didn't know that, but if you want to then open source the data set, you cannot use a commercial license model. So Mistral was the only option, but really interesting that that's the case. Anyway, so we used that for quite a long time with a lot of compute, and basically prompted the model to tell us what you cannot see in a satellite image. For example, you cannot see a border between two countries. That's existing in OpenStreetMap, but you cannot see it on a satellite image, so you want to discard that. There's things that at 10-meter resolution you cannot see. There will be things that are annotated like, I don't have a good example, stuff that is smaller than 10-meter resolution. And then we realized that the quality was still low, so we did some NDVI-based filtering where we basically said, if you have a mask, an OpenStreetMap, like this is a forest, then the NDVI within that mask should be pretty consistent. I mean, it's a forest, so the vegetation should be generally high. And outside of the mask, outside of the forest, then the vegetation should change, so the NDVI should be lower. So we basically said every time the NDVI is consistent within a mask and sufficiently different outside of it, we would consider that is a good mask. And every time it's not the case, we would just discard it. All of these are pretty rough thresholds. And we just designed them based on Benedict and me standing in front of a whiteboard saying, yeah, let's use 0.5. So when we open source the data set, we will also open source the raw data, and you pick all of the thresholds how you want. I think that's really important to say, because there will be a lot of potential to further improve the quality of the data set and remove noise by making better choices than we did. And then finally, we manually reviewed a subset with around 600 samples and 200 different classes in these samples for evaluation. So you see that there goes a lot of energy in that, and there goes very little energy in the model, what we will see in a second. This is how the data set then looks like. I mean, basically, it's some mask annotations on satellite images, nothing super unexpected. I want to talk about the model next, just to encourage everyone that you can do really cool research if you build a cool data set and you do a little bit of quantization. So consider that we already built this data set, and now we want to show the effect of the data set. So you don't want to build a super crazy sophisticated model that might have an additional increase. We want to keep the model as simple as possible to measure the effect of training on that data set. So basically what we did is we said we need some kind of model that gives us a mask. So the model should give us any kind of binary mask where you have, for example, is it water or no water? Is it forest or no forest? Is it airport taxiway or non-airport taxiway? For that, we just trained with a lot of binary masks that we get for free from OpenStreetMap, right? You would basically say every value in the mask is 1 and every value outside of the mask is 0. You will get that. And then you can use your favorite type of quantization, and you will end up with some kind of discrete tokens. And then you can do exactly the same. You input a satellite image and you train against these tokens. The only thing that we add on top is we want to interact with the model in a language way, because we might want to prompt only for a subset of the classes, for example. So on top of that, we have the text encoder here, which in our case is OpenClip, gives you latent representations, so just a couple of additional tokens that you would append to your set of latent representations from your encoder. You can condition your decoder on all of that. The mask tokens are just for the binary segmentation masks. You predict those, as we did in TerraMind all the time, and you get a binary mask mode. So everything that I want to say here is we trained TerraMind with quantized representations, and we could translate between modalities. Then in the paper that I showed with the temperature time series, very different data set, very sparse data cube, we could also learn correlations. You can use it for multitemporal, and it's particularly appealing because there you have very limited storage and memory for everything that you're training, because your data representations will be so compressed. There's a lot of open research going on, or not a lot, not enough, but a lot of cool research going on how to improve quantization, which is the FEDRA thing. And now here you can again see that even if you want to do something fundamentally different, like open vocabulary segmentation, which is really a new task, then you can do that too. So in order to leave, in order to show you a couple of examples how that would look like, this is how it would look like. So you see that often SAM and Dino kind of over-predict on certain areas, and the shapes are not really perfect. We are also missing some stuff, right? I mean, 30% MRU, you cannot do great on all of the images, but it's better than the others. Also, I mean, if we have 35% MRU, that means we have a lot of failure cases. So let's also talk about those. One of the most obvious ones are classes that we didn't pre-train
Just
on.
like the underwear and
Okay. That was kind of cute. Anyway, so you don't have cloud data in the data set, right? In OpenStreetMap, you wouldn't annotate clouds because you would annotate points of interest. So you don't have them in the pre-trained data set, you cannot identify them. Even though it's trivial in the spectral response, you can fit a model on that super easily. We cannot do it because it's not part of the data. Then same for words that have not been in the training data set. So terminal, for example. Terminal apparently was not in the pre-trained data set. When you have a satellite image of an airport and you prompt it for terminal, the model will do nothing. What I found pretty encouraging, though, was that it understands the difference, for example, between an airport, a runway, and the taxiways. So that's pretty cool, right? I mean, there are not too many airports in such a data set, and still it's pretty well able to do these things. So overall, mixed bag, not great. We can probably improve a lot. People could spend some work and annotate some clouds in the data set or some other stuff. So generally, I think there's a lot of really exciting things that you can do with the data set. And then you see, based on the concept of quantization, you don't need to change too much in the modeling. So you don't need to spend years on defining a new way of computing attention or something. And I feel like often the improvements on the modeling side, they're rather incremental, while with a new data set, you can often really unlock stuff. And you can here kind of see that you don't fundamentally change the way you approach a problem from a modeling perspective. If you have a new data set, you can still solve a new task. Okay, in order to leave a couple of minutes for questions, I wanted to wrap up with saying what I said before. So if you kind of unclicked after the first 3 slides, then this is basically the summary of the talk. Quantization helps you to learn across different modalities very easily. It can help you to stabilize the performance because you are mostly training in a cross-entropy scenario, which is often way more easy, especially if you scale up the number of different dimensions or representations. It can help you to approach new tasks quite easily because you focus more on the data set rather than doing something fancy in the model, which of course you can do too. And then we haven't looked too much into the embedding representation, but when you have a look at few shot performances of these models, then you see based on them being conditioned, like the patches being conditioned on the discrete representations, if you also have them in the input, that's pretty performant too. That's it. That's really it. Okay.
Thank you for interesting thought, Johannes. Does anyone have a question?
Yeah, a very general question, but do you know basically how much from a computation point of view this quantization is? Because you have to train the tokenizer, let's say, is another pre-training. So how much, if you do some sort of, if you have some ideas on, okay, it gives you way better representation, but you need way more computation. How, if you benchmark, let's say this, so when it's always worth to quantize, it's always worth to tokenize, or sometimes if you have small budget, and how much are these reusable for other tasks? So it's very wide question. So I hope, sorry, the experiment itself can attack, but
Yeah, me as well.
yeah. So yeah, but my question is just if you have some sort of, if you benchmark one against the other, so tokenizing with respect to performance and performance in sense, both. Yeah.
I think it's probably more that you can do stuff that was hard to do before, but it will not necessarily give you a computational bottleneck. You're more front-loading compute. So when I say in multitemporal, it's nicer because you have like way less memory pressure and you can feed longer time series. It's not cheaper, as you say, because you need to pre-train the other thing. You need to pre-tokenize everything that also lies in your storage, just not in memory. So I would say it's not necessarily good from a compute perspective. It might be better in some cases and worse in others, but we haven't really checked that. So I would not generally assume that it's way better or way worse. It will be somewhat similar, but it more helps you to unlock things that maybe are more difficult.
I have a follow-up question on that. On the compute aspect, since you convert the discrete tokens into embeddings, I mean, from let's say the amount of memory, etc. There's not a big difference between linearly projecting a float to an embedding or putting it in a lookup table and getting an embedding. I mean, and
Totally true.
And then because the model sees continuous vectors, of course. So maybe I missed that slide, but where is the computational efficiency benefit in the time series case or in the general case?
In the time series case, the computational benefit is not within the model. Let's say you have a model of 20 gigabytes lying in your GPU memory, you have a total of 100. Then you can just in data loading have much bigger batch sizes or longer time series, because what you input into your model for every patch where before you had 16 times 16 times the number of channels, you only have a single integer value.
So it's on the input then. Maybe
the I/O, the memory pressure on your entire system will be way lower, but not within the model and within the computational graph, as you said, because that's pretty much the same thing. You're only feeding different data. It's on these two sides here where data loading and to a certain extent also loss computation is a bit.
Data loading, let's say for the transfer of your data between CPU memory and GPU memory, you can imagine that it makes a difference. But also on the GPU, because you actually don't have the input, like you don't have the patches as input and not as targets, so maybe there's a small difference on the GPU as well. But I don't know if that's...
I think the main difference is data loading for the multitemporal thing. And there, I mean, if you have 16 by 16, 256, if you have 4 channels, then you have 1000x less I/O pressure.
I think people don't realize maybe often. I think more often than people realize the data loading is actually bottlenecking, not what happens on the GPU.
Yeah.
Or maybe.
I mean, like even there, I mean, it determines also what is in GPU memory, right?
Yeah.
So that.
Cool.
So in principle, it's a bit bold claim to say like you can fit a time series that is 1000x longer. Maybe not really, but maybe something like 10 to 100x.
But fit on the GPU.
Yeah.
So that means you have less GPU memory.
Yeah.
Okay, I thought the point was that the main benefit is in the transfer time.
That too. I mean, it's the transfer to the GPU, but then also like the data's on the GPU, right? So the data's in the GPU memory, and there also.
Yeah, but that's just the input and the output. So I would assume that fraction is quite small compared to all the data and the weights that are actually in during.
Depending on the batch size. I mean, it's true that, but let's say like I would say for most of the models that we train, we have around 20 to 40 gigabytes max GPU memory, and then we are maxing it out as much as we can, right?
Yeah.
GPU utilization and memory.
Yeah, but then the larger batch size also creates a larger intermediate data memory in your model, which is all the things anyway.
Yeah. And if you do that in the temporal dimension, probably too. No, it's true that there's a second interaction effect, but still on the pure data side that you fit in the GPU memory can be more. And even in the temporal dimension, it will not have an influence on the intermediate steps probably, because it would encode the temporal sequence in one shot.
Okay, well, that may,
and then
this of course makes it.
Yeah, that should also help.
Cool, but then X is huge. So
yeah, again, like
yeah,
take it with care, but treat it with care. But I would be confident that 10x should work.
Well,
and I would not say that it's necessarily more than that, but 10x I would say should be doable.
Okay, so first, thanks for the really and well, this quantization or discretization. I don't think I understand it very well. But, I can reiterate what you said. Just tell me if I'm more along the lines of how it's done. So, with this point of view of encoder autoencoder loss, decomposition of the autoencoder loss, and the discretization loss. So it's a natural decomposition, and the discretization loss, can we say it as basically some kind of a, however it's defined, a total distance between the points that we have inside the hypercube and the closest, the nearest vertex? Is it just the sum of the distances between those points to which we project?
That's a very good question. I never saw it that way.
Because I mean,
maybe that's true.
There's a thing that if you want to minimize this kind of distance, but expected distance, then actually, if we look at the data distribution in this hyperspace, right, we could, in general, do some, I don't know, rotations of the data and so on, so that globally the total distance from points to this discretization values is minimized, right? And it's a very well-defined problem.
Yes, that's exactly what the model is supposed to learn. And it's completely true that there's certainly a correlation between the sum of the distances and the loss. I'm just not sure if it's like a one-on-one relationship. Okay. You would say like 10% decrease in distance is 10% decrease.
No, not necessarily, but we are not interested in 10% of the difference, but to find a minimum.
Yeah,
right?
That's totally true. I mean, what the model tries to learn is, in the beginning, a randomly initialized model would bring the point wherever, and on average in the central of the hypercube. Then it would learn to project it into different areas. So think about it like you have this huge embedding space, and the model usually learns to build clusters. Now, the difference is that you project it into a hypercube and you tell the model to project it into the different areas of the hypercube. And by having the cube, you have the opportunity to build the closest distance to some reference point, like what you're missing in latent representation. That's the core idea. You're basically restricting your latent space into a hypercube.
It would be super cool to actually work a little bit and see on the data distribution in those spaces. For example, what's the effective dimension of such a set embedded in those high-dimensional spaces? Whether there are some kind of a concentration effects and so on. Because I mean, even with a standard, PCA technique, what you have is you have a data distribution and you try to find the, let's say, the directions which minimize the residues, right?
Yeah.
Between the directions and the data points. It's all about projection in this case, right? And you try to minimize the I don't know if it's an operator norm or whatever, but in the end, what you do is just to try to minimize residues. So maybe there is a way to somehow play a little bit with this geometry in such a way that it does minimize this how do you call discretization loss, right? And find, let's say, kind of optimal geometry.
It sounds like you're advertising our idea. Yeah, totally. I mean, I agree.
Yes.
Expect some cool work on that coming out.
Yeah, I just want to think of.
Yeah, no, but I think it's totally true. Like what fundamentally people assume is that the way you restrict your latent representation to build these kind of nearest neighbor relationships is fixed in a cube. And even if you don't have a cube, if you learn this projection to a latent representation, it's not fundamentally different from projecting in a cube. That's how they came up with the cube originally. So I do think that all of these things are quite unidimensional at the moment, how people think about it. So breaking this entirely and saying like, oh, it could be a sphere, it could be whatever, could be really cool.
Yeah, nevertheless, we don't know if it's actually worth it, right? To throw a huge machinery on the thing that will improve the loss a little bit and to actually not change results at all.
Yeah, totally.
But it's still worth looking into.
Yeah.
Yeah, thanks.
Cool. Maybe, yeah, go ahead.
Thanks for the question. I'm not very familiar with quantization and everything, but so I read TerraMind paper quite a few, like a long time ago, but I could remember that in terms of like generation between like the modality like optic and so on, the performances were not that good. I think, yeah, exactly, because between all modalities it was quite very satisfying. What I could remember is that between optic and SAR it was not the case. And is there like, why do you think it happens? Is it because like, do you have a way of like, I'm not familiar with quantization, but you have this code book, and do you have a way to just like try to see if you have a code book that actually doesn't encode so much or very redundant information or very compressed information? Because I don't know if you are using like fully polarimetric GRDs sentinel data, but for example, if you have mostly we have dual information like two polarization, and if you are using polarimetric composition, then it is not linked with the semantic class. Like, I mean, when you are using fully polarimetric sentinel, then you can discriminate class and have three class: volume, double bounce, and scattering. Like, I don't remember. But I mean, it's an average. So then you will try to find correlation with optic. But I mean, this is very poor information. And in the code book, you will mainly, I don't know if you have a way to check the really deep, like into this code book discretization. I don't know if my question is.
It does.
Because there's also the fact that the sentinel is very asymmetric. And so I don't know how it can, maybe if this is linked with redundant information, and if the redundant information will be in a very high in the distribution like that, then you will lose the information there. But they are still very important in stuff, because if you remove them, then the image is black basically, because everything is there. So I don't know.
All of that makes sense. It's two different dimensions. The first one, the translation between modalities, is a primary problem of correlation learning. I think it's less related to quantization, because basically, if you want to learn correlations between any kind of two things, you want them to be in a 45-degree angle. Like if they are like in vector geometry, if they would be parallel to each other, you don't need to learn correlations because the correlation is perfect already. So you would say every time I'm seeing that, I'm seeing that. If they are orthogonal, you cannot learn any correlation. I think SAR and optical are more orthogonal than parallel. So basically, I think regardless how you would try to generate one from the other, you will always, I mean,
So
it's kind of
from the modality in itself.
I think to a certain extent.
Yeah, that makes sense.
But it's still true that for the code book, it's very difficult to look into it because you always need to reconstruct, and there will be a long tail effect.
Yeah.
So the moment we are learning quantization, then the model will naturally allocate a lot of bins or different hooks to very dense areas, and for a long tail, we say like in digital elevation, everything that's over 2,000 meters is class high, and we'll just use that. So we actually see that, ironically, when you use TerraMind on the Alps, it performs terribly. But if you subtract all of the entire Alps by 2,000 meters. Performs great.
Okay.
So you can just see that it uses the very same
Yeah, exactly.
set of 2-3 tokens in the long tail. That's a big challenge.
Okay.
And it's pretty much unsolved. So hobby
It's
project.
interesting. It's really interesting. Thanks.
Cool.
Thank you.
Maybe we can give a chance to someone online to ask the question if there is any. Last question. And my laptop lost its battery, so if someone check the chat, or you can just take the.
I think we're already at
yourself
time.
and take the microphone. Did you hear me, people online? I don't know if I was clear. If anyone has a question online, feel free to put in the chat or take the microphone. Okay.
Not, maybe we can
Yeah.
just close.
Yeah. Okay. We're gonna assume that it was all clear like this. So
It
Johannes
was an
did
easy talk.
a great job explaining. Thank you so much. So thank you everyone for attending. Thank you, Johannes, for presenting. This was super interesting. Thank you, Cristiano, for organizing. Thank you everyone online, and see you next month. Bye bye.